Alright, so let's look at this problem. Search a 2D matrix. You can see the example basically says that the element in the last column of the previous row will be smaller than that of the next row first element. So it's basically a one-dimensional array, and it's just divided in 2 dimensions. So what you can do is that you can convert this into a one-dimensional array and then apply binary search, which would result in this log m cross n as well, but it would increase the space complexity by m cross n as well, because that will be the size of the new array. Instead, we will just treat it as a one-dimensional array but not use it physically. Okay, so let's start with this. It's same thing. First declare your low and high pointers, and my high will be, what will be high in this case? It will be m times n, which is, it's basically the number of elements. So what is m? M is my you can have it like, let me put it as column. This is column size, and n will be my row size, which will be matrix dot size. Okay, so it will be the same conditions. While low is less than equal to high, I will calculate the mid. What will be mid in this case? It will be the same thing, low plus high minus low by 2. If my matrix of, now here's the problem, right? You can't write mid. It's a two-dimensional thing. So what we will do is we will compute the index of row and column in this new, like we are treating it, let's say for the first time, since this is, look at this example, it's 12, right? Total, there are 12 entries. What will be the middle? It shows 6. So somewhere here, somewhere in this 11, right? What is the row and column number of this 11? The row number is 1 because it's this row, and the column number is also 1. Okay, so it's 1 1, but we had 0 1 2 3 4 5, it's 5. Okay, look at this 16. Row is 1 and column is 2. 0 1 2 3 4 5 6, right? So what do you see? How I know that if this is 6, if this is 5, then my row number is 1, right? And if this is 7, then my row number is 1 as well. But if it is 8, my row number becomes 2. So what is responsible for my row number? It's the length of columns, right? Length of columns. My column, I've treated it as m. So what will be my row number? It will be mid, which is my index, modulo my column numbers, right? And what will be my column? It will be mid divided by my m. Okay, let's see. What is 30 in this example? It's row number 2 and column number 1, right? What is its location according to the one-dimensional matrix? It's 9, right? So what is 9 modulo m? What is m? M is 4. 9 modulo m is 1. Is row number 1? No. Oh, sorry. It should be this. So row number, column number is 1 and row number is mid divided by my column. So it's 9 divided by 4, which is what? which is 2. So now I'll compute if this R and C is equal to target. What do I do? Alright, what do I have to return? I have to return true if it is found. So I return true. Else if this value matrix of R C is greater than target, this means that my target is on the lower end. So if it is on the lower end, which pointer should I move? I should move my high pointer. So high will be equal to mid -1, and similarly low is equals to mid +1. In the end, if nothing is found, then we return false and this thing terminates. Let's run it. Okay, so we are passing it. What is the time complexity of this solution? We are doing the same binary search. The length is m cross n, since it's all the element, right? So it's log of m cross n, which is the desired output. There is a brute force method of solving it. As I told you, just treat it as a one-dimensional array. Create a copy, make a one-dimensional array with m cross n size, and copy paste one by one, and then you can apply binary search. But that would incur a extra space complexity of m cross n. So this solution, it's logical. It's applying the same concept, but without using that extra space. Let's submit it. And yeah, we get